So let's look at our new test review packet. Morning. All right, I want to highlight the formulas that we need to know. So first off, there's no segmentation, no limit definition of area on the test trapezoid area. All right, yeah, we still need to know that one. So let me make sure I have that one. So we're gonna know the trapezoid area. Power rule for derivatives, trig derivatives. The hope is that you have these memorized, and then you can use this to help you do integral rules below, right? The trig integral rules. For the on the integral side, we have power rule for integrals. First theorem. That's just basically knowing that if there's bounds involved, you're going to find the antiderivative first and then plug in the upper and lower bound in that order, f of b minus f of a. And then the variations of first theorem, I think this will be more helpful when we get to the the calculator portion, especially this one here. Rearranging that first theorem formula, but we're not worried about that for this Friday's test. Second theorem says that if I am undoing, or if I'm applying an antiderivative and the derivative on top of a function f of t, that f is not going to change much. The only thing is that upper bound will get inserted into the function, and then the upper bound's derivative will be multiplied. So it has a little bit look of a chain rule thing going on here, but it's really because we're doing something and then we're undoing it, and in that process, that p of x gets impacted into the function, but that function itself is not going to change much. The trig integral rules, hope is that there's no need to memorize these, that you know you're just working backwards from the derivative rules. And then finally, average value theorem. Yeah.
What variations do you know those?
Oh, the variations, this will be good for the calculator portion, but not for the non-calculator. Yeah, this is all we need for the calculator. Any questions about these formulas? Yeah. Okay. All right, so let's do yeah, so these are various review sheets. Let's start with page 1, since this will hit a lot of the newer topics that we did last week. So let's start with okay, let's start with number 1. Number 1 says, given f of x equals x squared minus 2x plus 3, find the average value on the interval from 0 to 3, and then find the value of c. So we have to use average value theorem here. So average value theorem is kind of rearranging that height formula or that area formula of a rectangle. So we know that f of c, the height is just area divided by the width. And instead of saying area divided by width, we pull the width out in front and we say 1 over b minus a, and the integral from a to b of f of x. So when you memorize this average value theorem, this is the area component, that's the width component. Eventually, I'm area divided by the width equals the height. Okay, so given our function, find the average value on the interval from 0 to 3. So our function x squared minus 2x plus 3 will get inserted into f of x. What's our a and b value? Yeah, 0 and 3. So we just put everything into the formula, right? Okay, so this is basically 1/3. What should we do first? Do we plug the bounds into the expression? No, not yet, right? What do we do first? Yeah, find the antiderivative, right? We basically are moving from the right to the left, right? We're taking care of the antiderivative first, and then we can worry about the bounds, and then you can just multiply that 1/3 through, right? So you want to remove the bounds for now so that you can focus on your task at hand. Each term we can use what? Power rule, right? So x squared becomes x cubed over 3 minus plus now the bounds can come into play, right? Reduce a little bit here, the 2's can cancel out. Okay, upper bound first, right? Good thing about that lower bound is going to wipe everything out. So 27 over 3 is 9. 9 minus 9 plus 9 equals what? What does this add up to be here? Okay, just 9. Now we still have to make sure we include the what? Yeah, that 1/3, right? You have the area component, but you still got to make sure you don't forget about that width component. So 1/3 times 9, or 9 divided by 3 is what? 3. So this is my average value. Okay. So that means on this curve between 0 and 3, if I were to look at all the different heights along this curve, that height is going to average out to be 3. Okay, so then part B. Find the value of C guaranteed. So we know that the graph has a y value of 3, because that's the average height. But we're trying to figure out where does the graph actually reach that average height. So how can I find the location where the graph reaches that height? Okay, right. So 3 gets plugged into what of the function? The y value. Okay, yeah. So here, if I bring everything over to one side, the 3's cancel out. Factor out the x. So x equals 0, x equals 2. I have 2 c values. Are both okay?
Yeah.
Yes. So if it was first semester mean value theorem, we will have issues with the endpoint. The endpoint can't exist. But here, average value theorem, it's okay to have endpoints as part of our solution set. So 2 is between 0 and 3, and 0 is at the endpoint. So we have two locations where the graph actually hits that y value of 3.
So you can actually the endpoints too.
Endpoints you can keep. Yeah. Okay. Number 2, find the average value. So let's see if you can set this up. Okay, this one's is only asking for average values, so there's no part B to it. Just have to find average value. Okay, so we have our A and B, we have our function. Yes.
I think the other one, how can we do plus C?
Oh, whenever we have bounds involved, we never do plus C. We only do plus C if there are no bounds and you're trying to create a solution with a general solution. Yeah, so if there's no bounds, then you do plus C. If there's bounds, the C's goes away. It just washes out. All right, what can we do first here? Yeah, find the antiderivative, right? So what's the antiderivative of secant squared? Tangent. Yeah, we know that tangent's derivative is secant squared. So therefore, if I go backwards, antiderivative of secant squared bring me back to tangent. Okay, what do we use? What do we apply first? Upper bound, right? So tangent of pi over 4, then what? Comes next? Minus. Okay, so we cannot leave our answer like this. We have to evaluate. So we have to think about our unit circle values. So tangent of pi over 4, right? We know tangent is just y over x for sine and cosine. So what's tangent of pi over 4 going to be? Just 1, right? And then tangent of negative pi over 4, negative 1, right? So 1 minus a negative 1, what does that give us? 2. So is this our average value? That's the area component, right? We still have to worry about this coefficient out in front. So if I combine those together here, what's pi over 4 plus pi over 4? Yeah. So which is what? 2 pi over 4, which is pi over 2. And a pi over 2 in the denominator is same thing as what? 2 over pi in the numerator, right? So it's really 2 over pi times 2. Right. This is my width component that I cleaned up, so it's easier to work with. And then I have my area component. So area divided by the width gives me height. Okay, average value is 4 over pi. Okay, so we need to review our unit circle. Typically, I would say on the AP exam, whenever you're evaluating your upper and lower bound, on the AP exam, they will accept answer unsimplified. So they will accept your answer like this. However, the thing we got to watch out for is they will not accept this. Okay, so this is not far enough. You got to evaluate the trig down to a numeric value. Even though you technically evaluate the bounds, you got to go one step further. So I'm going to be expecting us to do this, and then same as AP exam, they're going to ask you to they're going to want you to get at least to this point before you can stop and earn full credit.
So you don't think it's like the 4/pi, you just get that 2.
Yeah, you could leave it as 2/pi times 2 if you want. Yeah, you could leave it your answer like this. That's fine. We just can't have any trig in our final answer. Right?
That's how you treat on a test.
Hmm?
Is that how you're gonna treat on a
That's
test?
what you're on a test. Yeah, I'm going to grade it the same way that AP exams would treat that problem. All right, so number 3, we have our function. Our function is this deft integral from -2 to -2x squared. We want to find the derivative of this. So what does that remind us of? What theorem are we going to apply there? Yeah, that's the second theorem. Okay, so we are doing two opposite processes on top of the function. And so this is the rule we have to follow. All right, we know that these two operations will cancel each other out. We just have to worry about inserting that upper bound variable into the variable of the expression. That's the first part, times the upper bound's derivative. So I'm going to write this out here. Essentially, I'm finding the derivative of this messiness, but we can avoid a whole lot of things because we're just doing and undoing something here. Right. So these two operations will cancel each other out. We just have to worry about how this upper bound is going to be involved with the answer. So what would the first part look like? So what would that look like for this expression? What does f of p of x look like? Take all the t values and do what? Replace it with that upper bound, right? Okay. So we're just doing a full replacement. Now, normally we cannot do this if it's a regular integral problem, right? Integral problem, we never can just plug that in, but here we can because we're basically undoing that process. So we're kind of back to this expression here. I want to make sure that we don't just do this for every instance. So that's the first part of second theorem. That takes care of the f of p of x times p prime. So times p prime times what? Yeah, -4x. Okay, I'm just going to clean this up a little bit here. Multiply the numerators together, I get 8x cubed. 4 plus 8x to the 6th. This is fine. Okay, number 4, also second theorem because we're putting a derivative and an integral on top of a function. But what's different about number 4? There's two variable bounds, so we have to repeat the process twice, right? So we'll do f of p of x and then minus, and then we'll do the same thing with the lower bound. So we just do the same thing above and below with what we did here. We just have to make sure we put a minus sign in between. Yes.
Do we also do the prime thing?
Yeah, we also do the prime thing.
Okay.
Yeah. Okay, so let me write out what we want to do here. Derivative. Circle. Okay, so apply second theorem. All right, upper bound first. Right, what would that look like? 1 minus. Good, 3x to the 1/2. All right. Times, okay, I'm not done with the upper bound yet, times what? That 3x to the 1/2 turns into what? Okay. Okay, so that takes care of my upper bound, right? Then we do a minus sign. And then we do what? lower bound in for the t, right? So 1 minus 2 times negative x, which is 1 plus 2x. Times what? Times negative 1. I'm not going to worry too much about the cleanup process. If you can have all the pieces there, I'll give you full credit. So any variation of cleanup is fine, but we just have to make sure we show all the steps here. You got that f of p of x times p prime minus f of q of x times q prime. You're repeating that process with what you did with the upper bounds because they're both variables. If one of the bounds was not a variable, then we can leave that part out. Okay, let's do even and odd functions. Number 5. Let me highlight the steps again with even and odd functions. The first thing we want to do is we want to graph the shorter interval first. Okay, or the shorter width. Okay, not the smaller area, but the shorter width. You want to look at the bounds to determine that. Second, you want to fill out the other side. The other side of the y-axis with what you know so far, right? If I have one part of the graph showing, if it's even, I'm going to duplicate it. If it's odd, I'm going to do equal but opposite. And then once you get as much as you can with that shorter interval, then you can bring in that larger interval, especially if there's an overlap. We want to make sure that we can evaluate what's happening with that overlap. So we can graph the larger interval last. Okay, first things first. Which one has the shorter interval? Second one. Okay. Now, there's something a little off about this. You see how the bounds are not in order? Typically, that's not an issue if we're just doing an integral problem. If this was flipped and we're just doing first theorem, it doesn't really matter if we flip the bounds. Things will work out in the end. But here, if we're trying to do something with a graph and something is out of order, then everything is backwards. So it's easier if we can rewrite this so we can just read from left to right. So how can I rewrite this so that this feels more straightforward? I can say from 0 to 3, g of x equal to what? Equal to 4. Yeah, so just watch out for that. If my bounds is out of order and you're trying to graph something, put it in order and then change the sign so that, because 3 to 0, negative 4 is same thing as 0 to 3, 4. This is really telling us it's above the graph, above the x-axis and not below, even though there's a negative 4 there. But because there's a opposite, I mean, the bounds are out of order, reading backwards, this is actually a positive 4. But it's easier if you rewrite it and see it that way. Okay, so we'll start with the smaller interval there first. So on our graph, part A is even, so it's an even function. Okay, so we graphed our shorter interval. What's next? Fill out the other side. What can we do about the other side? Okay, and what can we make it? Also 4, right? Because it's even. Okay, so now let's do the larger interval. Larger interval is from -3 to 6 is 10. Now, we don't want to do this. We don't want to, a lot of students want to do this. They want to say, oh, okay, this whole thing is 10. And then that just messes everything up because then you're overlapping something that's already been set. So we want to do this. Okay. So that's going to throw you off. What you want to do instead is you want to make a side note that, okay, I have portions that is filled out. I have portions that's not filled out, but ultimately everything has to add up to be 10, right? So I know that I'm going from -6 to 3, right? So this interval, my bad, -3 to 6. This was what's given to me. From -3 to 6, I know that this interval is 10. So I'm going to just put to the side that, okay, I need all this to add up to be 10. Right. So I have this, I don't want to be adding to this portion. This portion is already set. We don't want to be changing anything about this region. What we want to do is we want to figure out what is the missing region going to be. So if this is 8 and it adds up to be 10, this region must be what? 2. Must be 2. And if this side is 2, then this side is what? Also 2. Okay, so now we can figure out what the problem is asking for. It's asking from -6 to 3. So now shade in the parts that you want to add together. You have to never go from -6 to 3. G of x equals what? Yeah.
You don't want to switch. Like the final answer is 3 to -6, and the other one's -3 to 6.
Give me these two
Yeah.
here. This is what's given to us, and this is what they're asking for. Now, we can't assume that these are going to be the same, right? These are not the same regions. It's just kind of a coincidence. That's what you're asking. But yeah, basically, I'm not even going to look at what they're asking for until I fill out my entire graph. I'm just using my properties to fill out my entire graph, and at the end, I'm just going to total up what they're asking for me to add up. Okay, part B, odd function. And I'm going to use these properties to create an odd function. Okay, so initially, same steps. We want to start with the shorter interval, 0 to 3. Right, again, we're picking 0 to 3. We're picking the second one first, not because -4 is smaller than 10. We don't care about the area. We care about the width. Okay. Shorter width goes first. Okay, so from 0 to 3 is 4. Okay, what's next? Yeah, what's the other side going to show? -4. This is odd function, right? Okay. Now let's move on to a larger interval. Larger interval says from -3 to 6. This has to add up to be 10. I have -4 here, +4 here. We don't want to be overlapping with this region. We just want to figure out what is missing here. What can we say is missing? 10. Because -4 + 4 is 0. There's still 10 left over. 10 has to go with that region here. Okay, and if this is 10, what can I say about the other side? -10, it's an odd function, right? So everything should zero out if we were to add everything up from -6 to 6. But we don't want to always add everything up that we see in front of us. We're going to add up with the parts that they ask about. So we just care about from 0 to 6. What's our answer? Okay, so I want to point out 2 main troubles that students have with this problem, or with these problems on the test, is watching out, and sometimes students forget to watch out for the order of the bounds. And if you don't watch out for the order of bounds, if you graph that as -4, then that's going to throw everything off. Okay, and the second thing is students start overlapping when they shouldn't be overlapping. So make sure you follow the order. Shorter interval, fill out the other side, and then do your larger interval. Yeah.
The shortest one, second, you only have to switch the second one. You don't have to switch the first one.
No, I would switch both of them if they're both out of order. Yeah, we always want to switch the bounds if they're out of order, because otherwise, if you don't switch the bounds, this number may be misleading. You may be looking, it may be telling you it's 4, but it's actually -4. Does that make sense? So if the bounds are, if any of them are out of order, always swap them so that you can see, so that this number will be straightforward and not backwards. Does that make sense? Okay, good. All right, let's
Number always be on the bottom of the number.
yes, yeah. If we're trying to graph anything, we always want the smaller number at the bottom of the interval. Yeah, that way it's left to right, and this number is exactly what you would expect it to represent. All right, let's right, let's see how much of the second page we can do. I'm gonna skip number 6 and let's do number 7 here. Now, this is something similar to, okay, I think we did something like this yesterday, right? So let me skip this. Well, do you guys remember what's the u value for this problem? 3 over x, and then secant tangent, and then the 2 over x squared will cancel out, right? Okay, so this is, I think we did this already. Number 8 then. Okay, so let's go down our list of steps, right, in order. First thing is we always ask ourselves, can we expand and distribute our way and rely on power rule? What's the answer to that question? Can we do it? No. Order of operations, we can't distribute through a radical. This is, we need something more, we need more help than just expansion power rule. So U substitution is our next option. How can I rewrite to get that U value to show up? 5x times what? Yeah. Okay, what's our U value? 2 minus x. Okay, so I'm going to underline the parts that I want to replace. Is that x that's sitting out here? Will this cancel out on its own? No. So we know there's some additional step ahead of us. This is probably going to be a change of variable that we got to worry about. Okay, but we still want to let the U value be what's inside the parentheses. Okay, derivative. -1. Okay, cross multiply. All right, we're going to make my substitution with what I underlined. All right, what's the issue here? Yeah, the 5's okay. It's the x that won't cancel. We can't just, I see some students do this. They would either, okay, so there are 2 things that I see students do here. Students would say, okay, well, I'll just do power rule for this. And I'll do power rule for this. I'll do plus c and I'll end the problem. Okay, so we can't do that. Okay. Something else I see students do, they pull the 5x out. Think of this as just a coefficient, and then they make it 5x times -u to the 3/2, so we're 3/2. And they leave the x in the answer. Can't do that either. Okay, so I know this feels easier, but this is not the right way of going through it. we have to find a way to get that x to be in terms of u before we can move forward. So how can I find a way to get that x replaced? Yeah, we solve for x, right? We have something that we can use, and that comes in this form of u equals 2 minus x. If we rearrange this equation, we can solve for x and we can make the substitution. So if I rearrange this equation, x is equal to what? Minus u. So this has to go in here, and then we still have some algebraic steps ahead of us, because first, at least we have a pathway towards power rule, but things are still not going to be quite cleaned up yet. It is. Du over -1 is same thing as du times -1. So I find it's easier to just move that -1 to the top. Okay, so I want to distribute this through that 2 minus u, but I don't want to do it multiple times. So I'm gonna gather the negative, the u, and the 5 in front, and then I can just do it all together at once. Okay, any questions so far? Okay, so we're not quite ready for power rule, but at least we have a way towards it, right? Before we couldn't distribute, but now that radical is just with one variable, so we can distribute this without any trouble. So keep in mind, we haven't done any calculus yet, right? We're just trying to get to the starting line so that we can actually apply power rule. What's -5u to 1/2 times -u? Plus what? 5u 3/2. Also, I see some students, they get to this point and they circle their answer. They feel like they've gone far enough with all the steps they've taken, but we haven't done the calculus yet, so we still got to do power rule. Yeah. Oh. Plus 5, sorry, 5, sorry. Okay, good so far. Now we can do power rule, right? Okay. Right, we flip all the fractions up to the top, multiply by the coefficients in front, and then one more thing we have to do. Can this be our final answer? Okay, bring back what? Bring back your variable, right? Bring back your x. Your u is only a temporary variable. You can leave that as radical form or rational form, that doesn't matter, but we want to make sure we bring back what we started with. Okay, we're not going to do number 9. I just want to kind of walk through the steps. How would you approach number 9? Can we use power rule expansion yeah, we can, right? We can split this up into individual fractions. Do we do anything with the bounds at the beginning? No. Okay, so we basically set it up, we go through power rule, we evaluate, and then once we have our, once we take our antiderivative using power rule, then we can plug in the upper bound first minus lower bound. And once you get all your numbers in front of you, you can leave your answer all sprawled out. You don't have to clean anything up. As long as there are numbers, that's good. Okay. Okay. There's one major topic that I haven't gone over yet. I think I can go over that in the next 5 minutes. So in your test review packet, this is on page 9. Sorry, page 14. Page 14, number 9. Okay, we haven't gone over what to do with absolute value. So we know that this essentially is asking about area, right? But the nice thing about absolute value function is that it's going to create a nice geometric shape for us. And if we just figure out the width and height of the triangles, we can add the triangles up, and that's our area. Okay, there's no need to do power rule for these types of problems. I mean, we can, but that's not the, it's going to take longer if we did it that way. But first, I want to kind of talk about what does this graph look like? Absolute value of x plus 2. Basically, we're just trying to figure out what is the area under this graph, right? And we know that absolute value function graph looks like this, right? It's a V-shaped graph. And we just want to figure out what is the shape, what is that area underneath that between the x-axis and the absolute value function. Okay, so first thing is that if I set my expression equal to 0, that's where I'm going to find my vertex. So if I set x plus 2 equal to 0, x equals what? -2. That's where your vertex is. That's where the two lines will meet, and that's where the sharp point of your graph will exist. Okay, so sketch the graph. -2. It doesn't matter what your slope is. You just make it, just create a V graph from there. Okay, this is what your graph looks like. Okay, good so far. Now, we want to look at the region from -5 to 6. So see if we can count out to -5 and then to 6. And then extend your graph if you need to. So we're only looking at with the region between the graph and the x-axis. You're going to be forming two triangles. The triangles may not be the same dimensions, but it's okay. If we just figure out the width and height, we can figure out, add up but basically we're just doing this. The depth integral is just asking us to figure out what is the area of these two triangles. That's it. That's your answer. So this graph is y is equal to absolute value of x plus 2, right? That's the graph that we've created. Now, what's the area formula for a triangle? 1/2 base times height, right? Or width times height. Okay, let's do one at a time here. What's the width of my first triangle? 3, okay. What's the width of my second triangle? 8. Okay. Now, if I want to find the height of my triangle, I just have to figure out what the y value is at this point, right? So if I plug -5 in for x, and if I figure out what that number is, then that number is going to be the height. So if I plug -5 into the function to get this point here, what's -5 plus 2? -3. What's the absolute value of -3? +3. So the order pair here is -5, 3, and 3 will represent the height, will be the y value at this point, which will be the height of this triangle. Right? And if I plug 6 into the function here, 6 in for x, I get what? 6 plus 2 is 8. My order pair here is 6, 8. 8 is the y value. 8 is also the height of my second triangle. So if I add up the two triangles together, 1/2 base times height, 1/2 base times height. Okay, we'll get some more practice with this, but it's still easy. So as long as you can sketch out the graph and know that what the area of a triangle is, just adding two triangles every time. Okay, so help sessions. I will have help sessions tomorrow morning at 7:30, Friday morning, and also advisements today, tomorrow, and Friday. All right, come get your phones.